Hello, and welcome to the second in my series about trigonometry and its history. As usual, I imagine I'm talking mostly to other people who teach mathematics, and so I'm not teaching trigonometry here, but rather exposing some of my favourite ways of thinking of developing the subject, some of my favourite proofs, and of course the history, which I find absolutely fascinating. So here we are extending beyond right angles, triangles, and seeing where that gets us, and in particular what I've called the curious history of the cosine rule. You might even call it the troubled history of the cosine rule. It's quite different from the history of the sine rule. So the first episode was about right angle triangles, so we've done that. The other thing we need for this is coordinate geometry, Cartesian geometry, if you like. That, of course, is a serious anachronism because that's many centuries post-dates all of the trigonometry, in fact, that we're doing in this video. But nevertheless, it's by far the nicest way to do it, and all the best proofs come that way. So that's what I'm going to do. So in the first video, we just learned the definitions of the various trigonometric ratios in the context of a right angled triangle, where of course beta is always acute. So the question is, can we extend this idea to beta being bigger than 90 degrees? And at first sight, that seems a rather odd idea, doesn't it? Because after all, right angled triangles don't have angles bigger than 90 degrees. But this is an idea that happens a lot in mathematics. It's worth exploring a little. So you start with a simple definition in a simple domain, and then wonder whether you could extend the domain to something broader, and whether it would be useful to do so, and what you'd discover if you did. So if you do that, there's sort of three steps you have to take. One is to check that your new definition in your broader domain gives the same results as your simpler definition on the restricted domain. And then you need to check that some of the nice things that you've established in the restricted domain are still true in the broader domain. And then you explore and see whether this idea gets you anywhere, whether it's useful. So you meet that in a way first with multiplication, right at the beginning of school. So multiplication is first defined as repeated addition when you're multiplying two positive integers. And then you might say, well, I wonder if we could do this with negative numbers, and what would it be worth? And so we come up with what's essentially a new definition. There is no way that -2 times -3 is repeated multiplication. It's a different definition. So what we have to do is then check that our new definition agrees with the old one on positive integers. It does. Check that the nice things that we discovered about multiplication on positive integers are still true for integers generally, and those are associativity, commutativity, and the distributive law, and those are all true. And that's actually why we define negative multiplication the way we do, to make those things true. And then you need to work out whether this is going to get you anywhere. And of course it does. It opens up huge areas of mathematics. So what were the nice things we discovered here that we ought to try and preserve? Well, really only these two. So sine squared plus cos squared we discovered was always 1, and this complementary angles business. So we'd like those to be extended true. Okay, so let's see whether we can do this thing. So this is going to be our new definition, and it starts with a circle. So inside this circle, we have a little triangle, a right angle triangle with angle theta. And so in that triangle, this length we discovered was cos theta. In fact, that was one of the definitions of cosine, and that's the definition of sine, that length. Okay, so what that means at this point has coordinates cos theta, sine theta. Again, we're talking about acute angles here, and before we worked out what the graph of sine looked like, so let's just concentrate on sine for the moment. That's the y coordinate. So now we're going to go beyond 90, we'll go here. So now so sine now starts at 0, climbs up to 1, back down to 0, and then it goes negative, so y coordinate negative here, and it comes back up to 0. Well, there's no reason to stop there, is there? We can carry on forever. So angles can be bigger than 360. On the other hand, they can be negative, and it goes on forever. And that's what the graph of sine looks like. Already, we're seeing a hint of something much more important going on here or much bigger, shall I say, than geometry. This is a wave, isn't it? It looks like a wave. And the really exciting applications of trigonometry, or of these trigonometric functions, are to waves rather than geometry. And we shall come to that in a later video. But for now, the graph of sine looks like a wave. So does the graph of cos. Let's look at that. So that now, it's the x coordinate at this point. It starts at 1. Goes down through 0 to -1, and then back up to 1 again, and so on, round and round forever. So that's, and the graph's obviously much the same shape. No, so now we can look at the other ratios if we care. We don't much, but here they are. This is the secant 1 over cos. Now it actually, so there's an interesting thing here too, actually. So originally, secant was defined as essentially this length. And just as we've turned cos and sine from lengths into coordinates, we can do the same with sec. So now the secant is actually the coordinate at this point. So it climbs up from 1, whoops, here we go. It climbs from 1 up to sort of plus infinity, comes back from minus infinity, bounces off -1, and so on. So you can still see the old definition there, but it's now a coordinate, not a length. Well, and the cosec is the same, and tangent looks like that, and cotangent looks like that. You know all that stuff, don't you? Right, so that's our new definition. So the next thing we need to do is check whether these nice things we discovered before are still true. Okay, well, this one definitely is, isn't it? Because x squared plus y squared equals 1 is the equation of the circle, so that's definitely still true. That's very easy. The other one's pretty easy too, actually. So complementary angles, if this is the point parameterized by theta, and this is the one parameterized by 90 minus theta. So to get from one to the other, you reflect in this line, which is really theta equals 45. And that idea extends exactly around the circle. It's still true. You reflect, to get the complementary angle, you reflect in the line, this y equals 45 line, and that swaps x and y. So it's definitely true. These two definitely still true. And actually, this is quite a nice way to look at it. So cos of 45 minus theta is sine of 45 plus theta. And here we see the line y equals theta equals 45 on the graphs, and you see the symmetry there, that you reflect one of these graphs in that line, you get the other one. So there are two different ways of reflecting to see this one. Okay, so that's good. Now, does this stuff get us anywhere then? So, well, let's start with the cosine rule, because that's one of the first applications we meet of angles bigger than 90. And that's the version we know. Now, the interesting thing about this is how you prove it. So there are actually 3 cases to consider. There's the acute angle triangle. There's the one here where angle C is obtuse, and there's the one here where one of the other angles is obtuse. Now, an awful lot of proofs you see, both in books and on the internet, almost all the ones on the internet, ignore this possibility altogether. And some of those proofs are valid and some are not. So they don't acknowledge this as a possibility, and sometimes their proof doesn't work. So there are 3 cases here. Well, now let's look at a nice proof of this. Okay. So this is the nicest proof, I think. There aren't any cases. There's only one case, if you like. You don't have to divide the case up. So here's our triangle. We put C at the origin. We put A on this circle of radius B, and B we put on the x-axis distance A. So there's our ABC triangle. And it's not going to matter to us whether C is acute or obtuse, or the same is true of A. Look, here's A being obtuse, and here it's being acute. It really doesn't matter, because what we do is we say, well, we know what A is, that's the definition of sine and cos. We know what B is, that's even easier. And so we can work out the distance between them, and it's just that. And that works out to be that. So one case, absolutely the simplest proof. But we shall see that historically, it's not been at all easy to prove the cosine rule, or even to write it down properly. So anyway, that's interesting. So cosine rule is easy for us in the modern day. Now, what about the sine rule? Well, the sine rule is actually a bit more complicated, isn't it? Because you've got several different versions of it. This is the way it's often written. So these 3 quantities are all equal. If you cross multiply this equation here, you get that one, and that's the way in which it's often in fact used. But this one raises the interesting question: what is this magic length that these 3 quantities are all equal to? Well, you probably know it's twice the circumradius, isn't it? It's that. So there's another version of it which just says that. You don't often see that thing written as the sine rule, but it is really. So let's see how we prove that. So it's the same proof, essentially, almost the same. So we just need the y-coordinate now, actually, because so the y-coordinate of A, we've got the same setup. We've got this ABC with C at the centre. The y-coordinate of B is B sine C. That's the definition. And it doesn't matter where A is for that to be true. It can be anywhere. Okay, then And now the other thing is using angle B is a little bit more complicated. There's a sort of mirror image thing going on here, because this angle is sort of the wrong way round, but whether you take account or not of that, it's again clear that the y coordinate of B is c sine B, and again it doesn't matter where any of these things are. So that's again a very, very simple proof. The problem with that proof is it doesn't bring out this R business, and I don't think there's quite such a pretty way of doing that, actually. It's a little bit more messy, and I think you do need two cases here. So we start with just a circle of radius R, and then we put a chord in, which is going to be length A, and those are the points B and C. And we'll put in this other radius, and then we'll drop a perpendicular here and call this angle alpha. So now we see that A over 2 is R sine alpha. That's easy. That's just right angle triangle stuff. And that tells us that A equals 2R sine alpha. So now we put the point A in somewhere on this circle here. You know that the point at the center, that the angle at the circumference is half the angle at the center. So that tells you that A is alpha. And so A equals 2R sine A, and that's easy. Now, if you have A down here, on the other hand, so that the circumcenter is outside the triangle, well, it's not just that, actually, it's worse than that. The circumcenter is on the other side of this line from O. Actually, the previous proof works when the circumcenter is outside the triangle, so long as it's that side of like that. But here, well, there's some ways to do this, of course, none of it's terribly difficult. This is a cyclic quadrilateral, so A dashed is the supplement of A, and sine of A is sine of A dashed, and so A is 2R sine A dash. So the sine rule works both ways, but I can't see a really clean way. I haven't seen a really clean proof of this that doesn't split down into two cases, or doesn't assume something more sophisticated than we've got available to us. Okay, so that's the sine rule. Now, while we're here, let's do one other thing that's very similar proof. So we'll look at the area of this triangle. So again, we have same setup, exactly the same, C at the center, blah, blah, blah. A is the coordinates of A, as before with that, the coordinates of B are that. And so AD is the y coordinate of A is B sine C. And so the area of the triangle is half AB sine C. And again, it doesn't matter whether, it doesn't matter whether C is acute or obtuse, or one of the angles, other angles is acute or obtuse. It's because it's just algebra. It's interesting that these proofs become so very simple when you use coordinate geometry, and you can understand Descartes' dream in a way that he would want to reduce algebra to reduce geometry to algebra. Sometimes that really works very beautifully, and these are cases when it does. It doesn't always, of course, work at all nearly so nicely. Right. Let me go back to this picture now, that because there are some other symmetries that pop up from this picture which are worth looking at, that weren't there when we were just dealing with the acute angle. So one is, instead of reflecting in the 45-degree line, we reflect in the theta equals 0 line, and we get this one, and this is the theta equals 0 line too. And here we're keeping the y coordinate, which we're keeping the x coordinate the same, but changing the sign of the y coordinate. And so that gives rise to these symmetries, which you can see in this picture very clearly, that the cos is symmetric and sine is anti-symmetric. Then you can also reflect in this line, and that gives you these supplementary angles. And again, this is really reflecting the line theta equals 90. Let me just move that over so you can see that. So again, there's this 90 plus 90 minus thing. Okay, now then, there's another thing that comes out of this, which actually, to be honest, I'm not sure it's so terribly useful for geometry, but when we get onto waves, this is really very, very important. And this is the addition formula. So let's have a look at this setup now. It's a slightly different setup. We're on the unit circle here. Here we've got the point parameterized by the sum of two angles, alpha plus beta. And here we've just got F as 1, 0. Here we've got one point parameterized by beta and one by minus alpha. And that means these two angles are both alpha plus beta. And again, it's not going to matter where alpha is, whether it's acute or even, or even negative. It can be anything. The key point is that this point is parameterized by alpha plus beta and that by naught, and this is parameterized by beta and that by minus alpha. And so these two angles are equal. And so these two lengths are equal. So let's work out what those lengths are. So E, that's the point E, that's the point F. So the distance between them is that, which if you slog through the algebra, you get to that. Over on the other side, that's A, that's B. So the distance between them is that, and you bash through, you get that. Look at that to make sure that's true. And then that. And those are obviously equal, and so that gives you that. So that's a very slick proof of the addition formula. Much, much better, again, than most of the proofs you see. The purely geometric proofs often don't work for angles that, most of the proofs you see on the internet only work if alpha, beta, and alpha plus beta are all acute. So that's hopeless, whereas this works for any angle. So again, coordinate geometry is a real win here. Oh, well, we can bash through the other addition formulae. They come out just from algebra now. You don't need any more geometry because that is cos of alpha minus beta, for example, is cos of alpha plus negative beta. And that works out to be that because sine of negative beta is minus sine of beta, so you get a plus here. And this, you use the complementary angles business to work that one out. And similarly, you do that one. So that's all very easy. There are some special cases worth looking at here. So you can, out of that, you can recover the complementary angle business and the supplementary angle business. And this one, which is slightly different, which is saying that if you move something around 180 degrees, it changes its sign. Oh, and then we've got this business, doubling and halving, the special cases of 2 beta, and cos 2 beta and sine 2 beta. And, of course, we can do this in reverse. Let's have those ones. We can do this in reverse, and we get cos of alpha over 2 now. We just reverse this relationship, and so we can get those. Now, these are important historically because, we'll see, that's how we calculate all these trig ratios. So let's use them for our own purposes to calculate some more exact values. We know about 45, 30, and 60. Well, it's easy to work some more out using these formulas. So sine of 15, for example, is, well, it's sine of 45 minus 30. We use that formula and we get that. That'll also tell us sine and cos of 75. So we know sine and cos of all multiples of 15. We can then use the halving formula to get sine of 7.5 degrees if we choose. It's a bit messy, but that's what it is. And so we could work out sine and cos of all multiples of 7.5. And this is how Hipparchus worked out all his formulas, how he worked out his tables. So much of what we've talked about in this video was familiar to the ancients. Not the sine and cos rule, they're a little bit later. But the angles are bigger than the 180 business. I mean, really, that seems like quite a big step for us to move from, because we're starting with right angle triangles. But remember, the ancients didn't start there. They started here with what's called the chord function. So the chord of alpha is this distance here. So they were concerned, if you like, really, with the relationship between the arc length and the chord length. So chord chord of alpha is twice the sine of half of alpha. And so the equivalent of taking sine and cos beyond 90 is taking chord beyond 180. Well, that's not a big step, is it? I mean, it's obvious what that is. So going beyond that barrier, if you like, was not a big step for the ancients in the way that it is for us. Well, that's quite interesting. So most of this stuff was well familiar to them. And there we are. Those. So Hipparchus worked these out numerically rather than exactly, I think. Okay. So here's another one you can do. I haven't worked out cos of 3a, but it's easy enough to work out as cos of 2a plus 3a, and you get these formula. And then you can work out cos of 54 in this formula is in terms of cos of 18. You can also work out sine of 36 from the double angle formula. And it turns out these, of course, are equal because those two angles are complementary. And that tells you what sine and cos of 18 is. It's quite simple, actually. Quite nice. And then you can combine that with a 15-degree one and give us sine and cos of multiples of 3 degrees. And that's what Ptolemy did around 140 AD. So he started with this exactly what we're doing. I don't know exactly how he worked out sine and cos of 18, actually, but he did then do this halving business. And so he got multiples of, well, what the equivalent of sine and cos of multiples 3/8 degrees. He was actually using chord, of course. So it was the chord of 3/4 of a degree that he worked out multiples of. So that's really quite cute. Okay, now let's look at the history of the rest. So history of the sine rule is quite simple. Brahmagupta in India, he tabulated the sine function. He wasn't the first person to use the sine function. It had been used earlier in India. But he tabulated, I don't even know if he was the first to tabulate it, but his table survived. And he also discovered the sine rule. So that's the history of the sine rule, easy, Brahmagupta. History of the cos rule is altogether more complicated. If you read the internet, you will discover that there are people who think that Euclid discovered the cosine rule. That is actually rubbish. But let's look at what Euclid did discover, because it's sort of pre-cos rule in a way. This is Euclid's proposition 2 from proposition 12 from book 2. He writes this: so a squared is b squared plus c squared plus 2 times b times ad. Okay, well, that's an easy enough thing to prove. Here's the proof, because a is actually bd squared plus dc squared, so you can write all that down and it's an easy enough proof. And from our Olympian position of knowledge, we can see that ad is in fact minus c cos a. Euclid didn't know that because he didn't know about cosines, and he certainly didn't use negative numbers. So this is not trigonometry, it's a geometric theorem. And it's not trigonometry because fundamentally, trigonometry is about the relationship between angles and lengths. And there aren't any angles in this theorem, so it's not trigonometry, it's not the cos rule. So then there's proposition 13, which does the same for acute angled triangles. And it's interesting that it has to be done twice, this. And that's because of negative numbers. So from our point of view, we can see these two are really the same theorem, but AD, as it were, changes sign as it goes through here. If I go back to the previous version, you've got a plus 2BAD, and you go back to this one, it's minus 2AB. Because for Euclid, he wasn't dealing with numbers. He didn't know about negative numbers anyway, but he wasn't dealing with numbers. For him, these were lengths and areas, not numbers. And lengths and areas are always positive, at least as far as Euclid's concerned. So there's no way he could deal with these two propositions in one go. But interestingly, Euclid doesn't get it right, because he doesn't include the other cases where. So he deals with a case where angle A is either acute or obtuse, but when A is acute, he doesn't acknowledge the difficulties that might arise if one of the other angles is obtuse. In fact, his proof works perfectly well if B is acute, is obtuse, but it doesn't work when C is obtuse. So actually, he hasn't quite grasped the nettle here. He hasn't proved what isn't the cos rule. So he's a long way from having proved the cos rule. Okay, so where do we get started on the cos? Well, it's Brahmagupta again. So Brahmagupta tabulated not sine, not cosine, but versine, which is 1 minus cosine. And that has the great advantage that it's always positive. There's the graph of it for angles less than 180, 1 minus the cosine graph. So he might have discovered the versine rule, as it were the versine version of the cosine rule, which looks like this. So if you just take the cosine rule and substitute versine for 1 minus cosine, you get this. It's a really odd formula, isn't it? I mean, you look at it, b minus c squared, it starts with some other stuff. It's really a very counterintuitive version of the cosine rule. And so I'm not surprised nobody found it terribly early. I've never seen this formula, actually. Anywhere, I'm sure it's there. I'm sure it's written up somewhere, but it's not. It's certainly not widely used, not widely known. Of course, Brahmagupta might have discovered the cosine rule too, because he was the first person who really understood negative numbers and how to work with them and how to multiply them together and all that sort of stuff. So he'd got that taped. So he might have discovered the cosine rule, but he didn't. And neither did anybody else for ages and ages and ages, partly because although Brahmagupta got negative numbers under his belt, lots of other people never really got them right. I mean, Europe, negative numbers were still pretty iffy until the 17th century. And there were people then writing things like, negative numbers are nonsense, or perhaps, oh, well, yeah, you can have negative numbers, but of course you can't multiply two of them together. So Negative numbers turn out to be really, really hard. And that's one of the problems with the cosine rule, of course, because the cosine rule has a negative number in it. The cosine of an angle bigger than 90 is negative. So that, I think, is what really inhibited people in even discovering it. So here is a version of, again, you might recognize it. Of course, Al-Kashi didn't use symbols, he used words, and he talked about the sign of the complement, meaning what we call cosine. And he seems to have always assumed it positive. And of course, I don't actually know what he meant by the complement of an obtuse angle. We know that as a negative number angle, but did he know that? I don't know. So he sort of ended up with something horrible like this, or in the word version of this. He didn't say the modulus of the sign of the complement. He just assumed the sign of the complement was positive, so far as I can tell. So he needs to have two versions of the cosine rule, because he hasn't really got the hang of negative numbers yet. Even the word cosine appeared much, much later than all the other things. So this, I believe, is the first person who coined the word cosine, and indeed cosec and cotangent, I think. It defined it as the sign of the complement. But the first version of the cosine rule that looks at all like ours that I've been able to find is this one. And that's not until 1803, so fully 1,200 years after the sine rule. And it's in French. And here it is. There it is. It looks exactly like ours, doesn't it? But it took a long time to get there. So there we are, the troubled history of the cosine rule. Hope you enjoyed it.